Hi, my name is Sergey. Today I'm going to talk about what's happening with AI chips. So basically we'll have three parts. First, we'll discuss why we generally care about AI chips at this moment and what is sort of the practitioner view. Secondly, I'll discuss the concept of hardware lottery, how this influences this. And thirdly, we'll get a brief overview of what are the possible alternatives people try to introduce in the space. So yeah, let's get started. Now, the most important question here is why would we care? And actually there is a big reason to care at exactly this moment about the AI efficiency. So, as you know, for the past year or two, there's been a huge explosion in Gen AI interest. There's a lot of startups working in this space, a lot of products being launched, and it turns out that most of these products use NVIDIA GPUs. So here is the report from Sequoia Capital that says that data center revenue for NVIDIA is estimated to be around 150 billion by the end of this year, which is quite a huge number. And to make up for this loss, AI revenue actually has to go to 600 billion. Now, I'm not going to discuss here how are we going to make this money, because I have no idea. But I want to highlight the upper number, like 150 billion, and why this number could be much less, and how we missed this opportunity. Okay, so our main issue with NVIDIA GPUs is that they're very cost ineffective. Here we're talking specifically about data center GPUs. So here is an example. It's a recommendation from Tim Detmers, which is one of the top researchers in hardware these days, and he basically shows us a graph of relative performance of different GPUs, different precisions. Now, maybe hard to see it here, sorry, but generally the point is that everything looks here as expected. Like, the more expensive GPU is, the better performance you get from it. And and data center GPUs, because they're the most expensive, they're on the top of the chart, and gaming GPUs are lower. However, when they try to get this performance measured in terms of US dollar being invested, all data center cards move to the bottom of this graph. So it actually turns out that using gaming GPUs for deep learning training is very effective. And we're talking about orders, not orders, but I think it's like 5 times more efficient. I'll get to that. So to put it in another perspective, let me show some numbers here. So I want to highlight here, you don't have to take a look at all those numbers, just focus on the red squares. So what I want to say is that if we take a look at different GPUs that are available, for example, in the cloud, we will see that the main characteristic of those GPUs would be their GPU memory bandwidth. So it turns out that we do not care about that much these days about how much memory does a GPU have. Like, is there 80 gigabytes of memory or 40 gigabytes of memory or 24? We mostly care about what its memory bandwidth is. The numbers here are proportional. So the pricing actually reflects this common notion, because pricing, like the higher bandwidth you have, the higher pricing is for this instance, proportional. Pricing scales with bandwidth, not total RAM that we have in GPU. And in terms of this pricing, oh my god, it's so small. I'm sorry, I didn't know that the picture would be so small. So if we compare two kind of similar GPUs, one is L4, which we can use in the cloud. It's going to have a memory bandwidth of like 300 gigabytes per second and 24 gigabytes of VRAM. On the other side, we can have an RTX 4090. We can't use it on Google Cloud, but we can go to alternative providers like Vast or AI, and we can use it. So the bandwidth here would be 1 terabyte. So it's almost like a 3 times improvement. It's actually more than 3 times improvement in memory bandwidth. But the pricing for RTX 49 is actually lower than the price for L4. So here we see a potential, like, I'd say 6x improvement in terms of like our spend on GPU. So why don't we just use RTX 4090 in this case? Well, because NVIDIA knows about the fact that their gaming cards are much better in terms of performance than their data center cards. So there are multiple limitations with them. One is that I think it was like a previous year, kind of like this, NVIDIA disabled the support for NVLink inside gaming video cards. So NVLink means we usually use NVLink when there are multiple nodes. Like, let's say we have like 8 GPUs on each node, and there are like 8 different nodes. And to communicate between nodes efficiently, we need those kind of NVLinks. Otherwise, training or inference can be much slower. And secondly, NVIDIA disabled the support for kernel profiling tools. This is luckily not, because this one update was like done once and for all users, so it was very difficult to avoid this. This support this tool just means that if you have a newer CUDA driver version, CUDA toolkit version, you can't use NVIDIA profiling tools, kernel profiling tools, but you can do kernel profiling on gaming cards with older versions of driver. But again, like, given how fast things are changing, most people are not going to bother with it. Okay, so how does NVIDIA get away with all of this? Like, why aren't they already alternatives from different companies that offer similar quality of performance? The usual answer to this is that other companies do not have the software that NVIDIA has. The hardware of some companies is actually comparable, but the software is not on par. But I don't think that's the whole picture. Let me explain why. So there is this concept called hardware lottery. So what this means? Just as a brief summarization. So what we do if we are like AI developers these days is we write some high-level CPU code that gets transformed into more efficient CUDA kernels that by themselves call some specific bytecode. They basically compile to bytecode, or they use an MLIR for intermediate compilation, then MLIR converts into bytecode. So overall, this is like how things are getting done. And the concept of hardware lottery is that basically hardware lottery means that some research ideas may win just because they are better suited for available hardware and software than because they're just like fundamentally or theoretically better than some alternative research directions. So this is also known as Karenina's principles. Happy families are all alike. Every unhappy family is unhappy in its own way. So if something breaks, that means either hardware or software, that means we'll have a failure. So in terms of deep learning, there are actually multiple hardware lotteries that we're observing right now. First of all, we can get an overview of them by basically understanding a little bit about how GPU works, what is different compared to CPU. The main difference is that both are some devices that operate with some transistors, and there are computing transistors that are highlighted in green in this picture, and controlling transistors that are highlighted as yellow. And there is also some cache, but I'm not going to discuss it right now. So the point of GPU is that we're going to use only a single control unit for many different cores. And why is this good? Because this allows us to perform matrix multiplications pretty efficiently. So here is a different picture. Here I just want to show that there is specific tensor cores that, again, they correspond only to matrix multiplications. And here are some specifics. So again, I want to highlight just two points in this big table. You can take a look at this is specifications for 800 GPU provided by NVIDIA. You can take a look at the upper red box, which tells us that if we're using some general purpose chip, its operating speed is going to be around 20 teraflops. However, if we used to switching the tensor cores, am I right? I think that, yeah, that's fine. TensorFlow, yeah, this is highlighted here as TensorFlow. So what we actually see is we see an almost like 8 times improvement in terms of speed. So we have, at the moment, with GPUs, we have a very efficient tool to perform matrix multiplications. And basically, the task of any of most research teams these days, or deployment teams in AI, is to make sure that your computations involve as much matrix multiplications as possible. So you would try to avoid, drop away any other unnecessary computations. There are multiple points to that. One is the idea of kernel fusion, where you basically combine multiple operations to perform a single one. This is beneficial for memory bandwidth. The second is this idea of flash attention. So basically, again, why attention works compared to, maybe some of you know that there is a long, not a war, but let's say debate. Competition, yeah, between attention models like transformers and convolution models, which are respected by Yan LeCun. And the reason why transformers beat convolutions most of the time is exactly because it may not be a fundamental, like, theoretical benefit, but it's simply the fact that attention in its current version is involving a bunch of matrix multiplications, and what people do is that they write a very specific CUDA code, which is, again, like, CUDA is dedicated specifically to NVIDIA company, that optimize this flash attention to run as fast as possible by keeping in mind all of the restrictions. And the second idea here is that mixture of experts, they're also basically a way to bypass this limitation that we have in GPUs. So basically, these days, what we're trying to do is we're trying to you will get improvements in your money, like in inference price you pay, if you are able to introduce model that has better memory bandwidth under the same global GPU memory usage. So we're trying to maximize memory bandwidth as much as possible these days. Which gets me to the last point of my presentation. So what are the alternatives and why they may not catch up like that fast compared to NVIDIA GPUs? So this is generally related, again, just a short concept, because I think it's really important in the future. So there are separation between memory latency and memory bandwidth. So memory bandwidth basically means how much data we can push within a single transistor instruction, and latency means how fast we can execute those instructions. And the overall situation right now is that the latency lags behind bandwidth. So we can always squeeze out more bandwidth, but latency will suffer. The reason for that is that latency is basically limited by the speed of light that we have inside our wires that actually deliver signal. But bandwidth is something that it's like a width of our computation, and it's easy to scale. So we most of the alternatives to GPUs usually try to improve the last option. Yeah, and now just a couple of research ideas, or not maybe product ideas that have been introduced over the past years. So one is this idea of optical computing. It's actually quite nice in the sense that it promises to improve memory bandwidth significantly, because the way it works is by casting a light, a photon light, onto some, let's say, specific construction with lenses, and the point of that is you can like pack in really like big signals towards this computation. So it's kind of very cool for us, but unfortunately their problem is that they don't understand how to design learnable weights there. So they just use random weights. But I do believe that if this problem will be solved, then it will be like one of the best ways for us to move forward. The second idea is the most commonly discussed these days. These are the set of processors like united by the idea of MATML ASICs. So ASIC is a very specific hardware that is designed to perform like only a subset of instructions compared to GPU, which in theory can operate a much wider set of ops. I'm not gonna go into this scheme a lot, but generally the idea is that it basically tries to do what GPU does, but even more, in the sense that for a single control unit, we have even more those efficient like MATML units, which are called tensor cores or someone else. Yeah, and we can stack them together. And this improves bandwidth by simplifying units. This works really great for transformers-based architectures, but the problem is that other operations may suffer. And so here is the example for convolution operation. So in general, my understanding about ASICs is that they would be really hard to beat if we believe that in deep learning research, like nothing changes, that even like 5 years from now on, we will still use LLMs, we will still like use some high precision, so like 16-bit, at least 8-bit. And we believe that basically scaling this idea will solve all our problems. So this is actually, I believe, in part this is the path that OpenAI believes in. They have some investment in NVIDIA clusters, quite significant, but they also, like, I think Sam Altman pitched with some investors this idea of introducing alternative ASICs, and there are a lot of companies there, but their problem is that, again, they're usually overfitting specifically for transformer architecture, and also there could be some issues with software, which is what we discussed previously. And probably the last one interesting idea that I think can be promising. This is the idea of MATML-free computing. So here the idea is that we can remove bandwidth by dropping all multiplications. So we basically make all our weights binary, actually ternary. And yeah, this will require some new hardware that is not yet implemented. I believe it is in part connected to this idea of spiking chips, which is something that Sony has been developing a long time now, but it's not like a one-to-one mapping. But the problem of this idea is that it works only during inference. So we certainly do believe that specific ASICs or specific architectures that are optimized for inference will emerge, but regarding training it is not clear. And in general, I do believe that the question of can we train LMs without matrix multiplications can be like a very high, let's say it's a very important question to solve. But at the moment, the community takeaway is that we can train in 16-bit and convert most of the operations to 8-bit, which is not quite this 1.58-bit. Yeah, and finally, just an overview of how can we view GPU alternatives. This is an opinion by Thousand Chintala, which is, I believe, is a key developer in PyTorch, quite popular deep learning library, and they basically discuss. He basically presents his view of how to approach new AI accelerators. I can go over it if we have time, or if we don't have, I can.
I guess we don't have it.
Okay, sure, no problem. Yeah, thanks for attention. Here is the link to the slides. Feel free to reach to me. Yeah, there are some questions.
I have the first question. In this last slide,
yes.
Doesn't this thing resemble you actually the metric tensor changes coordinates? That, like
you mean this
physics?
one?
Yeah, physics knowledge. So you can have some. Mapping towards some universal coordinate system, yeah. And like imagine we have a LM now. Can't we just make all the weights binary and then sometimes add this prolongation or contraction of?
I'm not sure, to be honest. Again, I think some of this works during inference, and usually the way it works is that they take most of the weights and they convert them to some lower precision, but then there are also, because in LLMs we have some outliers, so there could be some weights which have a really huge number, unexpectedly huge numbers, and those we keep usually in high precision. And it's very difficult, especially when you start to scale model, it's very difficult to convert it to just.
Yeah, I know it's block-wise.
And, stuff like that.
No, but my idea is different. Like maybe we can, you can multiply, you can create big multidimensional tensor multiplications in binary, type trinary, but then change coordinates. So maybe I don't know, but I guess there is something.
Well, maybe it might be.
A nice idea.
Yes.
My question may be very amateur and maybe stupid.
No, it's okay.
I'm not expert in the field. I'm just trying
Me
to
too.
learn some stuff. Because, as I mentioned, we're trying to establish the AI center here. So again, the idea is to buy the GPUs, etc. Quick question regarding the comparison of RTXs and H100s. Yes, you said that the 4090s are more cost efficient. Yes, but if we're, for instance, if we're training the large models, llamas, for instance, which have what 65 billion parameters, which are manageable by 8100s, but if I recall correctly, 4090s can only run 6 billion parameters. So the benchmarking is clearly on the H100 side, so I don't understand whether there's a cost effectiveness there.
Yeah, they can actually, so it's an old problem, and there are some solutions to that. So I believe you should check out, first of all, this Galore paper. This one. So basically, yes, it happens, but you can solve this with some additional work. So in the most simplest way, what people do is there is this idea of model parallelism. So each device stores only, you launch training on
definitely like finite amount of something, and then you're running everything.
Yeah, but it's not just the data, it's also the model.
The model
So you
itself.
split the model across multiple devices, and this way you can fit more parameters in a single GPU. Yes?
So yeah, I have a question just to make sure that I understand correctly. So what did you say about ASIC and GPUs? So how I understood it, that we use GPUs more because they are more general models, and we can do more different operations on that. And that is probably the reason why they produce more GPUs than TPUs or ASICs or any other similar models, right? But if we see that transformers are the best architecture so far, we will see a rise of ASIC chips production in the future. Is that correct?
Yeah, and it's actually happening. I forgot to mention that there was this startup called Grok, which was created from previous engineers at TPUs, and they just built like an equivalent of TPU, and it's currently like one of the best accelerators in terms of speed to serve LLMs. But they're kind of closed at the moment, so you can't use them freely, but sometimes maybe they will open.
Yeah. Also, what do you think about like Max today give you authentic stock? You
Yeah,
mentioned
yeah.
that if you have at least 4,000 by 4,000 block, then you don't have a problem in communication between devices. So it was very surprising fact for me. And it also means that if you can put it is actually requiring small blocks into a GPU, maybe you don't need any links. Like, because as I remember in the links they give you like 10 or 1 to 10 terabytes between
You don't, so the common notion is that you don't need NVLinks if you are able to supply multiple chips. Like within a single machine, if you have 8 GPUs, they can work without NVLink. You need NVLink when you have multiple machines, and because they're physically like separated.
Yeah, I understand. I mean different. Like Max was talking about training and inference, like about propagating gradients. But they also were like Bloom. It is 175 billion. Like
Yes.
they used collapse to train parts of it. So they definitely put blocks there. So
Sure.
pipeline paradigm.
Yeah.
He said that actually after some blocks, like block sizes grow quadratically, and your like communication grows like cost grows linearly. So after some size, you have equilibrium, and this equilibrium is quite not so huge. Like he said, like 16 by 16K or over 4K. And so my question is like, this is interesting. So maybe you can actually do this without NVLinks. Yeah. But we need to check numbers, I think.
Yeah, I mean, maybe you can, but they won't hurt. But, you know, that's...
Okay. So do we have other questions? No. Thank you.